Okay, we're working on this one. Number one here, we have a block of sodium. Gives us the dimensions, 10 centimeters on the edge, perfect cube. What's the mass of the cube? And then I throw it in the water. Does it float before it blows up? It's highly reactive, so it actually wouldn't actually explode. So before it blows up, does it float? If so, what percent of the cube is out of the water? If not, what would be the weight of the cube if I were to weigh it underwater? Now, I'm not exactly sure what he means if I were to weigh it underwater, but I have a thought about that. So let's go ahead and start this problem. Okay, so oops, let's clear this away. And what we have here is a block of sodium that is 10 centimeters on a side. Now you have to look up, essentially, the first question is, what is the volume? Well, I think that's the first question. Oh no, what is the mass? Do you know the mass? Mass, that's one question. The other question is, will it float? Yeah, if the answer is yes, what percent is above the water? If it's no, what is the apparent weight? These are the questions that we're dealing with. So, first of all, we'd have to look up, in order to get the mass. We have the volume, but we need mass. So we need to know the density of sodium. And it turns out that's I did look that up, 2.13 grams per centimeter cubed. Now, if we had a cubic centimeter, if we had 1 cubic centimeter, which would be right down in here, that would be 2.13 grams. We have 10 by 10 by 10 cubic centimeters. So basically, we know the mass is equal to 2.13 grams, which is a single cubic centimeter, times 10 by 10 by 10 centimeters cubed. So we have a mass equal to 2.13 times 10 to the third grams. That is the mass of our block. Now notice that the density of water is equal to 1 gram per centimeter cubed, and we have 2 grams for the same volume, so we know this is not going to float. So to answer this question, will it float, the answer is no. And what is the apparent weight if it doesn't float? So I imagine that what he is asking there is if he weighs it underwater. So let's say we have water and we have this mass of sodium under the water, and somehow we have the ability to, hold up some sort of string here that's on a scale, and we're looking at what is the weight, what is this registering on the scale for this mass of sodium. So if what we know is that in order to figure this out, we know that, of course, outside of water, this would simply be the weight. If I were to weigh this, would simply be equal to the weight in air is 2.13 times 10 to the third kilograms times 9.8 meters per second squared, whatever that equals to, roughly 10. We were using 10. So roughly 2.13 times 10 to the fourth newtons would be the weight in air. Now, what happens when we put this in water? Well, what we know is that there will be a buoyancy force that in this direction, F buoyancy, and that force is equal to the weight of the water, or the weight of the medium that was displaced by this volume. So it equals the weight of the water that was displaced. So it essentially equals the weight of 1,000 centimeters cubed of water. So we know it's 1 gram per centimeter cubed. So we know it's 1,000. This is going to be equal to 1,000 newtons. Excuse me, 1,000 kilograms times, this is going to equal, I should really do this out so you can see what it equals. Hang on. Give myself some room here. So the force of buoyancy, by again, we're going on Archimedes' principle, which is that, here, let's see. When a body is completely or partially immersed in a fluid, the fluid exerts an upward force on the body equal to the weight of the fluid displaced by the body. So basically, the buoyancy force equals the weight of the fluid displaced by the body, whatever that is. So we know the body is 1,000 centimeters cubed, and we know that water is 1 gram per centimeter cubed. So we know this is 1,000. I'm sorry, I forgot to multiply by gravity, times gravity. So this is mass times acceleration. The mass is here. Mass, the acceleration is coming. Acceleration is coming. Times gravity equals 1,000 grams times roughly 10 meters per second squared equals 10,000, roughly. 10,000 newtons equals the buoyancy force. So this is the upward force. We know the downward force is simply the weight of this guy. This force equals the weight equals this weight in air. We figured that out as this number, 21,000 newtons. This is equal to 10,000 newtons. So this scale should read the net, so the net tension on the scale, if that's how he was envisioning it. I'm just guessing that. So we have a tension here, and this tension equals 21 kilonewtons minus 10 kilonewtons. So equals 11 kilonewtons roughly, equals the apparent weight of this object if it were underneath the water.